welcome to the deep dive. Today we're jumping right in, tackling how to search truly massive data sets. We're talking billions of items.
Yeah, think about finding like one specific thing in a haystack the size of a small country. It gives you a sense of the scale.
Exactly. And this isn't just theoretical, right? It's behind finding videos online or getting relevant web search results instantly from, well, trillions of pages.
Absolutely, because at that scale, finding the perfect match, the exact nearest neighbor, it becomes computationally impossible, basically, too slow. So that's where approximate nearest neighbor search, ANNS, comes in. We need results that are close enough, and we need them fast.
Which brings us nicely to today's source material, a research paper called SPANN, Highly Efficient Billion-Scale Approximate Nearest Neighbor Search.
Right. These researchers really went after this problem, searching billions of data points quickly and efficiently.
So our mission today is to really unpack SPANN. What are the key ideas? How does it offer this potential shortcut for huge searches without needing just tons of expensive memory? We're looking for those aha moments, you know?
Okay, so let's start with why the existing ways struggle. For smaller data sets, keeping everything in memory works great. It's fast, it's accurate.
Sure, you can just check everything.
But with billions of items, the memory cost is just astronomical. You'd need like server farms just for the index.
Wow. Yeah.
And that's why we need hybrid approaches mixing faster memory with much cheaper disk storage.
Right. And the paper mentions some older hybrid methods like DiskScan and HMANN.
It does. DiskScan, it tries to compress the data in memory, keeping the full vectors on disk.
But compression can lose information.
Right.
Affect accuracy.
That's the trade-off. You might miss some actual nearest neighbors. We call that recall, losing recall.
Okay. And HMAN.
HMANN avoids that lossy compression, uses different tiers of memory. But the catch is it needs a lot more of the fast, expensive memory, like 1.5 times more than DiskScan, the paper says.
And even their slower tier is still pricey compared to regular disks.
Precisely. So they were good steps, but both had, significant drawbacks, left room for something new.
Okay, makes sense. So there's this gap. How does SPANN tackle it? What's the core idea? It mentions using inverted indexes.
Yeah, that's the foundation.
Can you give us a quick refresher on inverted indexes? How does SPANN use that in this memory disk setup?
Sure. Think of a book index. Keywords point to page numbers. Here, SPANN groups similar data points together. These groups are called posting lists. Then for each group, it calculates a representative vector, a centroid.
Right.
And here's the clever bit. SPANN keeps only these centroids, the keywords, in fast memory. The actual data points, the posting lists themselves, live on the cheaper, slower disk. So when a query comes in, it first quickly scans the centroids in memory to find the most promising groups. Then it only pulls the relevant posting lists from the disk.
Got it. So you're not loading billions of vectors into RAM. That tackles the memory cost head on.
Exactly.
But managing billions of items on disk, that must bring its own headaches. The paper points out a few: posting length limitation, the boundary issue, and diverse search difficulty.
Yeah.
Let's take the first one, posting length. How do you keep disk access efficient if some groups are way bigger than others?
That's a huge issue. If some posting lists are massive, reading them from disk takes ages and you lose your speed advantage.
Right.
So SPANN uses something called hierarchical balanced clustering, or HBC, when building the index.
HBC.
Instead of one big clustering step, it breaks the data down iteratively, specifically trying to keep the final posting list roughly the same size. Balanced.
Makes sense. Keep things even.
And the paper notes this is way faster computationally than trying to balance it all in one go. They also use a representative vector, the one closest to the centroid, for the in-memory index. And they use a specific in-memory index called SPTag to make searching those centroids super fast.
Okay. Hierarchical balanced clustering. Got it.
Yeah.
Now, the boundary issue. Figure 1 in the paper shows this. How can you miss a neighbor?
Right. Imagine your query point lands right near the edge of a cluster, a data group.
Okay.
Its closest centroid might belong to Group A, so SPANN searches Group A's posting list on disk. But the actual nearest neighbor vector might be just over the line in Group B. And if Group B's centroid wasn't quite close enough to make the initial cut, SPANN might never look in that posting list. It could miss the true closest match.
Ouch. Yeah, that sounds like a potential accuracy hit. How does SPANN try to prevent that? Catch those boundary points?
They use a technique called posting list expansion, or more technically, closure multi-cluster assignment.
Multi-cluster assignment.
Right. Basically, when they're clustering, if a data point is close to multiple centroids, meaning it's near a boundary, They assign it to all those nearby clusters, not just the closest one.
So it appears in multiple lists.
Yeah. The paper mentions they found assigning it to, like, at most 8 nearby clusters, if the distances were similar, was a good balance.
Improves the chances of finding it then.
Exactly. If any of those lists it belongs to get searched, that boundary vector gets considered.
Okay, that makes sense. You're casting a wider net for those tricky ones.
Yeah.
But wouldn't that mean duplicating data, making the lists bigger, slower to read?
Good point. That's a definite concern. And they thought about that too. They optimized this using something called the RNG rule,
RNG.
Relative Neighborhood Graph Rule. It's basically a way to trim redundancy. If a boundary vector is going into list A, and list B is really similar to list A, their centroids are close, the RNG rule might say, okay, don't also put it in list B.
Why?
Because if the lists are that similar, you're probably going to search both of them anyway if the query is in that area. Duplicating the vector doesn't add much value, but adds cost. It keeps the lists leaner.
Clever. Okay, so we've got HPC for list length and this closure assignment with RNG for boundary issues. What about the third challenge? Diverse search difficulty. Figure 2 and those FT1M stats. What's that about?
Yeah, this is interesting. It's just the reality that some searches are easy, some are hard.
How so?
For some queries, the nearest neighbors are all tightly packed together. You might only need to check a few posting lists. For others, the neighbors are scattered, and you need to look much wider, search many more lists to get good recall.
Right.
If you just search, say, the top 10 lists every single time, you'd waste effort on easy queries and probably not search enough for the hard ones, hurting accuracy.
And the SIFT1M stats really showed that difference.
Dramatically. Like 80% of queries needed only 6 lists searched for the top result, but 1% needed up to 114 lists.
Wow, okay. Huge difference. So how does SPANN adapt? It can't just search 114 lists every time.
No, definitely not. This is where query-aware dynamic pruning comes in.
Query-aware, dynamic pruning. Okay.
Instead of a fixed number, SPANN looks at how close the query is to the centroids it found in memory. It finds the single closest centroid first. Then it sets a dynamic threshold based on that distance. It only bothers reading posting lists from disk if their centroids are almost as close as that very best one. The paper gives the formula involving an epsilon parameter.
So it prunes, it cuts off the lists whose centroids are relatively farther away for that specific query.
Exactly. For easy queries where neighbors are close, it searches very few lists. For hard queries, it naturally searches more. This saves a lot of time in I/O, especially on the easy ones, without really hurting recall because the closure assignment helps catch boundary cases.
This all sounds really well thought out, but, theory is one thing. How did it actually perform in experiments?
Against the competition. The results look pretty strong, actually. They tested it against Discan, a major competitor, on 3 huge billion-scale data sets, SIFT2-1B, Space EV1B, Deep1B. SPANN was consistently faster, like about twice as fast to hit 90% recall, using the same amount of memory as Discan.
Twice as fast. That's significant.
Yeah. They gave an example, hitting 90% recall in around 1 millisecond with just 32 gigs of RAM on these billion-point data sets. Figure 6 in the paper shows this pretty clearly.
1 millisecond. Wow. That could really change things for real-time application.
It really could. Faster, more efficient retrieval on massive data.
Okay, so that's against another disk-based method. What about compared to the pure in-memory algorithms, the ones that are usually faster but need tons of RAM?
Good question. They did that comparison too, using the smaller SIFT2-1M dataset so the in-memory methods could actually run.
Right.
They introduced this metric, VQ capacity. It kind of combines vectors processed and queries per second, looking at overall efficiency considering memory too.
Okay, a sort of bang-for-your-buck metric.
Sort of, yeah. And figure 7 and 8 show SPANN had the best VQ capacity compared to top in-memory methods like NSG, HNSW, SCAN.
Even though its raw speed per query might be slightly slower due to disk access.
Exactly. Its overall efficiency, especially when you factor in the memory cost, which is often the real bottleneck at scale, was superior. It highlights its practicality for large systems.
And they did ablation studies, too, to
Yeah.
isolate the impact of each technique.
They did. Very important for understanding why it works well. They looked at the hierarchical balanced clustering first.
And did it make a difference compared to simpler clustering?
Oh, yeah. Figure 10 shows HBC gave much better recall and lower latency compared to just random centroids or basic hierarchical k-means. Balancing those lists really matters for disk I/O. And they found HBC itself was pretty fast to compute. They also looked at how many centroids to use. Figure 9 suggests around 16% of the points as centroids seemed optimal, a trade-off between memory for centroids and search performance.
16%.
Hmm.
Okay, what about the ablation for the other parts? The closure assignment and dynamic pruning.
For closure assignment, putting points in multiple lists, Figure 11 showed using more replicas helped performance, but yeah, there was a point of diminishing returns. Around 8 replicas seemed best, which is what they used.
Sensible. No need to overdo it.
Right. And for the query-aware dynamic pruning, Figure 12 confirmed it cut latency further, especially at tighter latency budgets without really harming recall. So that dynamic adjustment based on query difficulty, definitely valuable.
Really interesting how all these pieces fit together. And you mentioned it's designed with distributed systems in mind, too, like spreading the search across many machines.
Yes, that's a key aspect.
Oh.
The whole idea of only searching relevant posting lists works really well when distributed. You don't need every machine involved in every query.
Ah, okay.
They explain how the balanced clustering and closure assignment can work across a cluster. And they even use a smart bin packing algorithm based on past query patterns to distribute data and expected query load evenly. Avoids overloading specific machines, those hotspots.
Did they show results for that distributed setup?
They did. On the Space EV1B dataset, figures 13 and 14 show SPANN distributing data and queries much more evenly than just random partitioning.
So fewer machines get hit per query.
Exactly. Instead of potentially hitting all machines, SPANN might only need to query a small subset. This means lower latency, less network traffic, lower overall cost. They quantified the resource saving at around 80%.
80% resource saving. That's huge for large-scale deployments.
It really is.
Okay, so wrapping this up, SPANN seems like a genuinely powerful approach for this massive nearest neighbor search problem.
I think so. The key takeaways are, high speed, high accuracy, but with significantly lower memory costs compared to alternatives at that billion scale.
Driven by those core techniques.
Right. The hierarchical balanced clustering to manage disk I/O, the posting list expansion using closure and RNG to catch boundary cases accurately and efficiently, and that query-aware dynamic pruning to optimize search effort per query.
And it feels like a big statement, too. The inverted indexes, maybe seen as older tech by some, can be revitalized like this.
Definitely. It shows that with clever design, especially around data layout and selective searching, this approach is still incredibly competitive and scalable. It's a strong alternative to purely graph-based methods, especially if you're watching your budget or memory footprint.
Yeah, very compelling. This has been a great deep dive. It really makes you think about any system dealing with similarity search at scale. What new things become possible when you can search billions of items this efficiently. It definitely opens up doors. Thanks for digging into this with me today.
My pleasure. It's fascinating stuff.